Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Today's presentation will focus on cost-effective approaches using colloidal zero-valent iron for in-situ groundwater remediation. With that, I'd like to introduce our first speaker for today. We are pleased to have with us Mr. Rick Gillespie. Mr. Gillespie serves as Senior Vice President in North America for REGENESIS, directing a team of technical sales consultants and engineers across North America, providing industry-leading support to REGENESIS customers. He has over 20 years' experience in the environmental remediation industry. All right, that concludes our introduction. So now I'll hand things over to Rick to get us started.
Thanks, Dane. I'd like to personally welcome each of you to today's webinar. I know how valuable your day is, and we want to say thank you for making time in your busy schedule. Our entire team is pleased to bring you today's webinar on colloidal iron for in-situ groundwater remediation. Our purpose today is to train on the power and efficacy of utilizing zero-valent iron to promote in-situ chemical reduction, often referred to as ISCR. Our goal will be to provide details on how best to harness this remediation technology to achieve results at your contaminated sites. Today's webinar comes at one of the most exciting times in our company's history. We are experiencing significant breakthroughs in the use of colloidal remediation materials like plume stop, our liquid activated carbon, and now colloidal zero-valent iron. These remediation approaches are changing the way we treat groundwater. They are being used to achieve permanent reductions in contaminant concentrations to gain regulatory closures at significant cost savings over traditional technologies like pump and treat. But let me pause there and introduce today's speaker, John Freim. John brings a distinguished track record to his new role as Director of Materials Science at REGENESIS. With over 30 years of experience in materials processing, John and his colleague, James Harvey, will lead our effort to build our first state-of-the-art colloidal manufacturing facility right here in Southern California. John will be responsible for leading our milling and manufacturing for not only colloidal iron products, but also our other groundbreaking colloidal product lines like plume stop. This fully integrated production facility, combined with John's deep technical expertise, will fuel our continued growth in bringing the best technologies to the environmental industry. Our partnership with John started several years ago, where we worked together on the utilization of micron dispersible iron with our current product lines, including plume stop and 3D microemulsion. Prior to REGENESIS, John served as the president of On Materials. His firm specialized in the manufacturing of ZVI products that were used at several hundred product applications across the US. John has a Ph.D. in materials science from UC San Diego and a BS in chemical engineering from the University of Illinois at Urbana-Champaign. He has been awarded several research grants from the US EPA, Department of Energy, and the US Air Force. John currently serves on review panels at the National Institutes of Health that's responsible for reviewing new environmental technologies. With that as an introduction, John, let me hand the webinar over to you.
Okay, thank you, Rick. I'm honored to be here today at REGENESIS. I'm going to talk about using colloidal zero-valent iron to accomplish in-situ remediation of chlorinated contaminants. So we've been doing this at On Materials for about 17 years, and in the last 17 years, I've been working with colloidal iron in many forms to try to optimize the material and take it from what was originally commodity material and then make it an engineered material for remediation. So let's give you a little bit of background here. This might be a review for a lot of people, but where did the chlorinated solvents come from in the industry? A common thing is dry cleaners. PCEs use it as a cleaning agent in dry cleaners, and there's a lot of spills, unintentional and intentional, that have occurred. If you talk about people that do site investigation, if you ask them where the most common place for a PCE spill is at a site, is at the back door, where people had thrown stuff out the back door in the past. That's one source of contamination. You know, there's industrial facilities that use PCE, TCE, 1,1-TCA, degreasing, cleaning, adhesives, etc. These sites number in the thousands across the country and across the world. There's also a lot of chlorinated contamination at aerospace and defense installations, where they were used to clean planes, weapons, missile silos, etc. So if you look at the universe of chlorinated solvent contamination, you know, there's several thousands, if not tens of thousands, sites across the U.S. and the world. So how do we get rid of these chlorinated contaminants? As you well know, most of these are pretty recalcitrant. The natural attenuation is generally pretty slow. So if you want to bring your site to closure, you generally have to be aggressive and work on some sort of remedial option. There's, you know, more or less 3 or 4 general classifications that we can use. One is direct push injection, where you use temporary injection points, inject your remediation amendments into the subsurface. You can also use permanent wells, which would be similar to your monitoring wells, which might have a screen section somewhere down in the aquifer that's contaminated. And of course, there's mechanical options, which would be something as simple as excavation, or something a little more elegant, such as soil mixing, where you bring your remediation amendments into contact with your contaminants. So why use zero valent iron? What does it have to bring to the table that other approaches don't have? Well, one thing that's really interesting about iron is that you can address the contamination through a couple of different mechanisms, and I'll talk about these more as we go forward. But one of them is chemical reduction, which is actually the direct reaction of the iron with your contaminants in the ground. It's also called abiotic reaction. Additionally, you can also have enhanced bioremediation. You can also have these things in parallel, and we'll step through these as we go forward in the webinar. One thing that's really important with ZVI is that when you engineer it and you make an advanced material, you can use it in a manner which satisfies all the requirements for successful in-situ remediation. And I call these the 4 cornerstones, and we'll walk through these as we go forward. In general, with in-situ techniques, you're not going to have to use excavation, permanent system installs, such as vapor extraction systems. Everything happens in the ground. You inject the stuff once, and the remediation occurs. So this is kind of the premise of what we try to do when we design remediation amendments. I call these 4 cornerstones. When we design our projects, when we design our materials, you really have to take all 4 of these in consideration. If you don't have success or consider all 4 of these individually, there's a pretty good chance that you're not going to have success. The first one is reactivity, and that's what most people consider about when they talk about remedial amendments. Obviously, the material has to react with the TCE or whatever your target contaminant is, but that's really only one step of the process. On top of that, if you go down to the bottom, there's the green little circle there. It's distribution. And those of you who've been in the industry for a while have heard the terminology, it's a contact sport. And that's really true. If you don't, you can have the most reactive material in the world, but if it's not brought into contact with the contaminants, there's a pretty good chance you're not going to have a successful outcome. So when you design your injection event and your materials, you need to take into consideration distribution. The third cornerstone is in blue there. It's called persistence, or it might be also called longevity. If you have a reactive material but it doesn't last very long, it's not going to do you a lot of good. You can end up with rebound, etc. And the example might be, hydrogen peroxide, really reactive in a bottle, but the half-life might be minutes or hours, and it's generally not going to do you a whole lot of good in the long run. And don't forget about easy use. You want something that's easy to use and safe. So what I'm going to do now is kind of step through each of these 4 cornerstones and talk about them a little bit more in particular. So let's start off with reactivity. This right here is a little stick diagram showing the chemical formulations of PCE and its daughter products all the way down through ethene. Those of you that are familiar with bioremediation know that it's a sequential process. PCE is reduced to TCE, subsequently reduced to DCE vinyl and to ethene. And in this case, you basically take one chlorine atom off your molecule and then replace it with a hydrogen molecule. The good thing that's really great about iron is that you can actually use a different reduction mechanism that bypasses, or at least largely bypasses, these daughter products. So what ends up happening is that your parent compounds, which are typically PCE and TCE, are reduced directly to ethene through these chloroacetylene intermediates that you see down here in the bottom. So for example, PCE is reduced. It's a 2-electron process, just like the bio process, to dichloroacetylene, which is a short-lived intermediary. You go to the right, you get chloroacetylene, once again another short-lived intermediary, and acetylene. And what's really, really nice here is that you bypass, vinyl, and vinyl often is more toxic with lower MCLs than your parent compounds. So it's a really good feature of iron that you can get that you don't necessarily get in bioremediation. So let's talk about some other reactions that occur in the subsurface. Sorry if this seems like chemistry class, but sometimes it's unavoidable to have these formulas up here. This top equation that starts with 5-FeO, which stands for zero valent iron, is a balanced chemical reaction for iron with carbon PCE, C2Cl4. And you can see when you have a full reduction, you get oxidized iron, C2H6, which is ethane, and your chlorides are reduced. And that's what you really want to happen when you put your iron in the ground. You want to reduce your PCE to something that's innocuous, in this case ethane. But there's another reaction that also can happen, and there's actually several, but the primary one that we need to consider is the reaction of ZVI with water. ZVI is a very, very powerful reductant, and it's capable of reacting with water to form molecular hydrogen, and that's the bottom equation there. And although the molecular hydrogen can be beneficial, it can be used by the microbes that assist in doing the biological degradation of the contaminants. It's not a direct reductant. You don't get a reaction with molecular hydrogen and your contaminant to form an innocuous byproducts. And even in a highly contaminated site, there's a lot more water around than there is the PCE, for example. So every molecule of iron that reacts with water I consider to be kind of wasted. So our objective, and what we try to do when we engineer our remedial products, is to maximize the reaction with PCE relative to the reaction with water. So how do we do this? Well, there's been a lot of research in the last few years on how to optimize ZVI for the chlorinated reaction with chlorinated contaminants. And this actually isn't new. This work actually began in 1995 approximately. And what people did was they actually sulfidated the surface of the iron. And what they found is that when you sulfidated the surface of the iron, you form a core shell structure where you have iron, which is still the bulkier material, in the middle of your particle. But when you deposit an iron sulfide layer on top of it, a lot of good things happen. If you look here on the right, this is a graph which was taken from an ES&T article that was published about a year ago by Fan et al. And it's really striking. If you look at these bar plots, the left is bare iron, bare ZVI. And what these researchers did was they measured the relative amount of the electrons or the iron which went to reduction of water and compared it to the amount of iron that went to the reduction of the TCE. And if you look at it, it's, the upper 90% of the stuff actually is kind of wasted in producing hydrogen, and very, very little of the iron went to reducing TCE. What has been discovered is on the right side of this bar graph, you can see that's sulfidated iron, and it's exact opposite. The sulfidated iron really doesn't react with water. So what that allows you to do is have all your electron efficiency go to the TCE. You get much, much faster reaction rates, much better efficiency and reactive capacity. And it's really been a groundbreaking revelation that we've learned and really come to recognize in the last couple of years. Another thing it does is it allows us to make an aqueous phase ZVI product. The reaction with water is passivated, so we can actually make colloidal iron in water. So this is a treatability study that we did here in the last few months. And what I'm trying to do here is verify the results that have been published by Dr. Fan, Dr. Tretnek, et cetera, at the other research areas. There's people at Texas Tech that do this as well. And I compared CARBONYL iron, which is unmodified. It's dry iron straight out of a can. And I dosed it in a bottle with about 6 milligrams per liter of PCE, and compared it to our Aqua ZVI product, which is a sulfidated colloidal iron of about the same size. It's a little bit smaller than the CARBONYL iron, but for comparison, they're relatively close. And compared the reactivities. Now, one thing that's different about these two studies is that I learned that to get good reduction in a month or so with CARBONYL iron, I had to add 50 grams per liter. With Aqua ZVI, I only had to add 2 grams per liter. And if you look at the reaction progress over time, and you run through the kinetic analysis, you can see that the sulfidated iron has got about, on a mass basis, about a 30 times enhancements in reactivity with PCE. And this data that we did in-house is corroborated by stuff that's done by other researchers. So it's really revolutionary how much faster, by adding just a couple mole % of iron sulfide to the surface of the iron can enhance the reactivity. So I'm going to change course here a little bit and talk about reactivity in regards to biodegradation. And instead of having your beta elimination pathway that bypass the cis and vinyl, when you do metal cis bioremediation, at least one of the pathways that occurs is more traditional. You have this stepwise sequential reduction of your contaminants. And this is, instead of just injecting iron into the ground, it's a little more of a complicated potion per se. Just step back here. Excuse me. There's a mixture. You add iron, with the purpose of the iron is to make the groundwater reducing. Usually get a ORP of -200 or less almost immediately, and also deoxygenate it, and also promote some abiotic degradation. You add organic donors, which provide a long-term source of molecular hydrogen. Water, it's an aqueous phase process. We generally recommend adding commercial dechlorinating cultures. Sometimes you have to add pH modifiers. This process works better at a neutral pH. And when you add all these things together, you get a really, really fertile environment for biodegradation. If you look on the right there, there's a portable ORP meter in the concoction with a little bit of everything put together, with the ORP of -400. And I'll talk about a site where we applied this in a little bit here. So that's kind of the first cornerstone that we've considered in our process, reactivity. So now I'm going to try to segue a little bit here into delivery. How we engineer our materials so they can be delivered to the contaminants. And like I said earlier, it's a contact sport. You can have a really, really reactive material, but if you can't get it in the ground and bring it into contact, you're not going to have a successful remediation program. So a key feature of small particles, iron is dense. The specific gravity is about 8. And if you put it in water, gravity is going to take control and the stuff's going to sink. But one thing we have, on our side is that smaller particles are buoyant. They still settle, gravity still acts on them, but they settle at a much slower rate than a larger particle size will. For example, if you increase the particle size by a factor of 10, the settling is going to decrease by a factor of 100. There's a square relationship there. So what we try to demonstrate here in this slide is that there's Aqua ZVI in water, 2 to 3 microns, and we just literally pour the stuff in a bottle, shake it up, and you can see it suspends. On the right, there's coarser iron, 40 micron approximately, put that stuff in a bottle, shake it up, and you can actually physically watch the stuff settle with your eyes. This demonstration's done better in person than on a slide, but this still illustrates the problem that you have with these larger irons. And they're really not all that big. If you look at them, they kind of look like flour or sand. You can't really even see the individual grains. But since iron's so dense, the stuff does settle and it gives you problems. So if you want to inject the smaller stuff, the colloidal stuff, it's really easy. You just pour the stuff in water, put it in your mixed tote. You can inject it right into the ground without generally having to add any sort of additives, organic additives. When people do conventional microscale iron, you generally have to add thickeners. Guar is a typical one that's used. End up with a thick suspension that artificially keeps the larger particles in suspension, and but there's problems with that, as we'll see here on the next slide. So stay on the topic of delivery. What I'm trying to do here is compare the characteristics of the suspension and the delivery of a colloidal iron system compared to a microscale iron system. So on top, that's aqueous EVI that's being poured into a fish tank, and we removed the fish beforehand, so don't get PETA on me here. Fish went into another bowl before we did this test. But anyway, you can see how the stuff blooms. Very little agitation. If you've seen the plume stop demonstration or marking literature, it actually behaves quite similarly and looks the same. And you go to the right of that, there's a sandbox demonstration where we're at a low pressure, we're injecting the suspension into a sandbox, and you can see there's a nice uniform front. The particles are small enough they can fit within the grains of sand in the interconnected pore space, and you get a nice uniform distribution of the material. Compare that to a thickened microscale slurry on the bottom. That's a picture of thickened iron actually in a grout pump, which is a really inelegant way to inject iron. But when you have something thick, you actually have to use high pressures because the stuff's not going to go on the ground unless you really, really force it mechanically. And if you look at the right, there's a depiction of an injection well in the ground where a thickened microscale iron's being injected. And you see that you have, a heterogeneous or inhomogeneous distribution. You get channeling, you get fracturing, and the problem with that is that you actually have areas right here. If you look at the pointer, in between the areas where the amendment has been delivered, where you don't get anything delivered. And the problem with that is that the stuff that's in there is not going to get in contact with your iron or your other amendment. It's not going to you achieve your remedial goals. Sometimes what happens when you have this sort of situation is you intersect the screen on the monitoring well, and the iron or your other amendment goes into the monitoring well and sinks to the bottom, and they test it, and everything comes back peachy keen. But then you might do a confirmation well by DPT a few feet away, and you more or less have unaffected treatment. So that's delivery. Don't take this for granted. Delivery is every bit as important as reactivity, and if you don't have both of them together, you're not going to have a successful project. All right, the third cornerstone is persistence. As I said earlier, you want something that's going to last. You don't want something that's going to be around for a few hours and maybe a day or a week, then be reacted away, and then you're going to have rebound and a lot of other problems. And this is, for those of you that are familiar with NZVI or nanocrystalline zero valent iron, some people have called this stuff champagne powder. You put NZVI in water, it actually bubbles like champagne, and that's actually the iron reacting with the water to form hydrogen, and it literally just boils away in front of your eyes. So what we try to do is, through using slightly larger particles, instead of using nano, which is 0.2 microns, we're using 2 microns. Gives you persistence, and also sulfating the material also reduces the reaction with water. This plot here is a repetitive spiking test that was done in REGENESIS, taking aqueous EVI and doing repetitive spikes over looks like about a 5-month period, and this test is still ongoing. Each of these spikes is about 10 milligrams per liter, and a half a year into this, you can see that there's continued degradation with very, very little reduction in the reactivity. The orange plot is a control. You can see it's kind of taken off. So that's persistence. We'll get to the fourth cornerstone of our remediation goals, for lack of a better term, is ease of use. Iron traditionally has been delivered dry. It's in super sacks or cans, and because of that, it's not easy to work with. You have to use forklifts or expensive or intricate powder handling equipment. You have dust, you have inhalation hazards, which is common to use in any sort of dry powder. And what we try to do is by making the materials instead of in a liquid suspension form, is alleviate those problems that are associated with the handling of dry powders. And there's, on the right is a picture of a ladle of aqua metal or aqua ZVI, which, it's a couple thousand centipoise, really, really easy to handle. If you have it in a pail, you can just dump it into your mixed tank, or it can be pumped using double diaphragm pumps or other similar equipment. And more or less, you just have to use your standard PPE, such as safety glasses, etc. But you're not going to have to use full-on respirators or whatever, because there's not issues with dust. It's also not issues with using heavy equipment to move this stuff around. Really, really, really simple to use. Just add the material to water, pump it in the ground, and you're on your way. All right, so I'm going to try to do is tie everything together here. I've talked about reactivity, persistence, delivery, etc. And what this is a neat little plot here that shows the functions of particles of the iron is a function of particle size. So we're going to start off here on the left and go to the right. The left are smaller materials. I'll start with soluble iron, which would be ferrous iron solutions such as CRS that's sold by REGENESIS. We'll go up a little bit larger to nano ZVI, which is typically about 0.2 microns. And we'll scroll across to the near microscale, which would be the REGENESIS products, aqua ZVI and micro ZVI. And as we go to the right, we get to larger materials. So this red plot here talks about the ease of injection, and I'll get back to that here in a minute. Let's talk about kinetics first. Generally, stuff that's smaller has more surface area, so it's more powerful kinetically. It reacts more rapidly. So nano ZVI here on the left, a lot of surface area, reacts really, really quickly. And as you go across this plot to the right, and you use the powder ZVI or the millimeter, the cast iron, the scrap iron, not very reactive. The next thing here I'm talking about is persistence. This is kind of the yellow line here, and it's the inverse relationship with reactivity. Stuff that's small is short-lived, and stuff that's large lasts a longer time. And if you look right here in the middle, you kind of got a sweet spot. It's right here where my cursor is right now. What we found for ZVI and actually other remediation amendments as well is that you get down to the near microscale area, a micron or two, you kind of get the best of both worlds. You can get good reactivity, but you can also get persistence. The red plot's not quite so simple. That talks about the ease of injection. So we'll start off here on the left. Soluble materials, easy to inject. If you can get water in the ground, you can get these in the ground as well. But you have a little bump here when you talk about nano ZVI. And this has been one of the problems that people that did NZVI, 10, 15 years ago, when it was kind of in vogue, is that they couldn't inject this stuff. And people that are involved in material science, that have done ceramics like me for 30 years or whatever, the answer to that's actually pretty simple, and it's agglomeration. Small particles tend to clump. There's a lot of surface area, there's interparticle forces. So you, instead of injecting discrete nanoparticles that are 0.2 microns, which theoretically should be easy to inject, you end up injecting much, much larger clumps or aggregates. Kind of the analogy I like to give is instead of injecting a single grape into the ground, you inject a bunch of grapes. And because of that, people had really, really suffered on getting good distribution. When you go back to our sweet spot, to our near microscale regime, 1 to 2 microns, the particles are actually large enough where the agglomeration issues become much, much more manageable. You can use dispersants, etc., to keep these things from agglomerating, and because of that, you get much, much better distribution and material that's easier to inject. You do have to do a little bit of mixing and recirculation because of the effect of gravity, but it's very, very gentle. You get up to powdered ZVI, 30, 40 microns, for example. Gravity starts to really become a big issue. And the other issue is that the particles are actually larger than the pore space in the sand particles where you're trying to inject it into. So more or less to apply the powdered ZVI via injection wells or in situ, you're going to have to use some sort of high pressure technique or possibly soil mixing as well. And if you're using the really, really big stuff, soil mixing or trenching is the only way to make it happen. But the key takeaway here, I'm trying to combine the 4 cornerstones on one plot here. If you look right here in the middle, 1 to 4 microns is really where you want to be. It provides the best of all worlds. Let's talk about the different types of iron that are available on the market today. I'll start off on the larger stuff in the bottom, and we'll work our way up. Cast or scrap iron is big stuff. You can actually see the stuff with your eyes. It comes from a crushed car, for example. I'm sure some of you have had a car that's broke down on the side of the road, and you realize it's going to cost more to fix than it's worth. So you call the towing guy. He goes, "All right, title for $300." You say, "Okay." Hand it off to him, and it ends up in the crusher. And it's very possible that that car, which was my '97 Windstar, by the way, ended up in a PRB someplace. So, it can work, but that's more for your mechanical applications. You go up to what I consider to be more engineered irons. Several vendors of commodity iron, somewhere in the range, 40 to 100 microns. Stuff's powdered, kind of looks like flour. Smaller side of commodity iron would be, there are specialty grades that are, say, 3 to 10 microns, which is starting to be where it's easier to work with. It's still about 3 times the size of our colloidal products, but they start to behave more like a small particle size material. NZVI is 0.2 microns. There's a TEM micrograph of a NZVI material right up here on the right. And just for comparison, soluble materials, which aren't solids. So how do we inject these different types of materials? How do we use them for remediation? The smaller materials, soluble amendments, NZVI, colloidal iron, can be done through either screen wells, which is really a good feature. If you want to do multiple injections, or you want to use existing infrastructure, the material is small enough where it can actually be injected through the slots of PVC or wells, or sometimes there's other ways to do it using sampler screens. You can also use direct push. There's many different types of tooling involved where you can get the stuff distributed into the ground. If you go a little bit bigger to the commodity irons, you have to use fracking, you can use soil mixing, etc. I'll run through a couple examples of the applications of colloidal iron in the field. This is a site in Florida, which was a 1,1 DCE site, which is somewhat unusual, but that's the pairing compound. The contractor decided to do this straight abiotically, didn't add any bioremediation amendments or microbes. The middle skid there is actually calcium carbonate. We did buffer this site. The native pH was about 5. We want to get that above 6, where the reactivity is optimized. So the red areas are where the contaminants are. And monitoring results were very, very positive. There's like 8 or 9 sites, 8 or 9 monitoring wells on this project, and all of them, were in the green area where we had environmental compliance with the state. And on this left well, the results are pretty striking. We started off 200 ppb. At the end, it was more or less non-detect. So this is an example of an abiotic degradation. There's no daughter products. It goes straight to either ethene or ethane. All right, the next slide here is a little more interesting. This is a metal-assisted bioremediation project in Texas. This is, if you've seen my webinars before, or seen me give this talk in person, you've probably seen this before. That machine there that says GOF is a vapor degreaser. This site, they were rebuilding alternators, and the degreasing was part of the process. And these guys at the plant, they went home on a Friday, came back on a Sunday, and this thing had ruptured. And there was about 200 gallons of TCE that spilled onto the floor. And they came back on Monday, the paint was peeling from the walls. Now you'd bring in full hazmat, have the fire department there, have EMTs there probably. Well, back in the day, they really didn't know any better. They just had like the janitors come with squeegees and squeegee the stuff into a trench, and they just started working again. So yeah, 200 gallons of TCE, about, there's the aquatar about 10 to 12 feet down, and it had been sitting there for 20 years with little or no natural attenuation. This picture, we actually got this from the wall of this plant. They had closed it. They moved the manufacturing overseas. I guess it was cheaper to make new alternators overseas than it was to remanufacture them. And the people that left the building, their parting shot was to take a picture of this and post it on the wall. So a little bit of a legacy there. We used metal-assisted bioremediation, colloidal iron, organic donor, pH modifier. There's slightly acidic, so we want to get the pH up. Nutrients, dechlorinating microbes. Kind of hit this with the kitchen sink. So this is the monitoring results in one well near the source zone. What's really important to realize here is that, initially in 2008, before this program was done, TCE was 4,300 micromolars, which is about 400 milligrams per liter. So you're talking about really, really contaminated groundwater. Obviously DNAP was still present. The initial program, there's maybe about 60 injection wells, I'd say, screen wells where the injection was done. We had a colloidal iron organic donor, and it really, really good result of getting rid of the TCE. You can see it went from 400 milligrams per liter down to less than 5 probably. But the problem is that we converted most of it to cis. On a molar basis, it was more or less a 1-to-1 conversion to cis. So we talked to the customer, talked to some of the consultants that were involved in bioremediation, did some tests, did a much smaller program a couple years later where the focus was to get the pH up. It was in the 5s. We wanted to get it, above 6, where bioremediation happens the most effectively. And we also added the dihalococoides, and sure enough, it worked really, really well. Within about a year after the program, the cis was gone. There was a nice little neat spike in ethene, which you rarely see in the field, an ethene spike this large. It almost looks like a bottle test. And we have data out to say 2016, and 5 years later, everything was below MCL. So, metal-assisted bioremediation is really powerful. If you do it properly and add all the components that you need to make things work, you can have a successful outcome. All right, I'm going to segue to the REGENESIS product suite. Right now, there's 3 iron products that are available. Aqua ZBI is a water-based amendment, which is engineered pretty much strictly for in-situ chemical reduction or abiotic degradation. It's 40% iron sulfidated, 2 to 3 microns in water, And what's really neat about this is it can be co-applied with plume stop. We've done several bench studies, and it actually is very, very synergistic and does not affect the absorption properties of the plume stop. If you want to do a metal-assisted bioremediation project instead, you can use micro ZVI, which instead of being suspended in water, the material is suspended in glycerol. This will give you a mixture of ischor and anaerobic bioremediation. Iron's basically the same, about 2 to 3 microns, and the stuff can be co-applied with organic amendments such as 3-DME or whatever you want to use for your project, and dechlorinating microbes. On top of that, there's the legacy product, which is CRS, which is a soluble ferrous iron solution, which does promote ischor, and that's a process called BIRD, or biogeochemical reductive dechlorination. If you have any questions about that, you can give me a call. So as Rick said earlier, REGENESIS is invested into a state-of-the-art colloidal manufacturing facility in San Diego County. And right now we're setting up to manufacture the colloidal zero valent metal products. We should have full-scale production, within a couple of weeks. And on top of that, we're going to make plume stop there and other colloidal products that are in the pipeline. We're also going to do R&D there. We're not going to rest on our laurels and try to improve the products, come up with new things, and try to stay on top of the state of the art. So we're getting down to the end of the talk here. As a summary, there's a picture of me up there on the right, by the way, doing my best field impression. I've been called Bob the Builder more than once on sites, by the way. So I guess the yellow vest and the hard hat makes me look like Bob the Builder. I haven't had kids that age in a while, so I'm not real familiar with that show, but I take their word for it. And by the way, that's James Harvey with an injection trailer, showing how the stuff's mixed and applied. So in summary, ZVI's been around since probably the 80s, actually. But in the last, several years, we've really tried to take the base technology and engineer it to make a good technology and make it great. And that's by reducing the particle size, sulfidating it, adding the organic additives that make the stuff suspend well. And you can never, go back to these 4 cornerstones enough: reactivity, delivery, persistence, and ease of use. What we really try to do is provide a product and a technology which will take into consideration each of these 4. So at the end of the day, you're going to have a successful project outcome. And that is it for my part of the webinar.
So thanks, John. Let me just start off with an apology. We had some audio issues up front. We want to make sure that those were addressed. If it makes you feel any better, they were probably twice as bad for me as they were for you. So we all experienced the feedback. We're going to move into the question and answer period. If you're not familiar within the app itself, there is a place for you to ask questions. We have several that have come in so far, but I would encourage you to submit those questions now. Every question that is submitted, we will answer. So if we don't get to your question, just rest assured that we will respond to you directly within 24 to 48 hours. So we've got a great group of folks, from end users to regulators to consultants. We'll get a broad range of questions. I'll start with one of my own. You showed a couple of different examples. Some sites where ZVI was standalone, some sites where it was metals assisted bioremediation in conjunction with donors and bioaugmentation. Could you maybe speak to the decision-making process on where you might use one standalone and where you'd use it in combination with other approaches?
Absolutely, Rick. That's a really good question. As we talked about earlier, ZVI is really, really reactive with the parent compounds. So if you have a site that's mostly PCE or TCE with maybe a limited amount of natural attenuation or degradation, that's a really kind of a prime candidate for using straight abiotic reduction or chemical reduction. If you look at the reactivity with iron with vinyl chloride, for example, it's actually not as reactive. So in those cases, we found that microbes, if they're applied properly and have a good fertile environment, are actually more are better capable of reducing vinyl to ethene. So if you have a site with a mixture of daughter products, it's probably better in that case to use metal-assisted bioremediation. There's also a few contaminants that don't react very well directly with iron, DCM, 1,2-DCA, trichloropropane, for example. And in those cases, it's better to use bioremediation.
So we're getting a few questions related to distribution, which we both agree is key to any remediation technology. Could you maybe speak to what type of radius of influence you can expect? They've given an example here of 10 to the minus 3 centimeters per second in a fine sand. I know it would range on the different types of lithologies you're injecting into, but what are typical radius of influences for this material?
We have kind of our default well spacing is somewhere about 15 feet typically, which translates to a radius of influence of 7 to 8 feet. We found that over the years, if we keep our well spacing 15, 20 feet, there's a really good chance that we're going to get uniform subsurface distribution. There are cases where it's physically impossible to have wells that close together. It might be infrastructure involved, etc. And if needed, you can use larger spacings. You just have to put more material into each well.
Kind of distribution application question. Are there any special handling requirements for ZVI? Are they stable under atmospheric conditions? Do they need to be stored under anaerobic conditions? Kind of walk us through that process of delivery, meaning to the site, and then application at that field site.
The material is engineered to be easy to use, so it's shipped in pails. It's not shipped under a nitrogen blanket, for example. You do want, for the aqua ZVI, you probably want to avoid freezing if possible. If you have an application where you actually might experience cold weather, it'd probably be better to use the glycerol-based material. It's also probably better not to store the stuff, above 100 degrees Fahrenheit for an extended period of time. But at ambient conditions, you should be able to have a shelf life of months, if not even longer, up to a year. As far as handling, just use common sense, standard PPE, and there's really nothing that out of the ordinary that you have to do to be safe. The fact that the material is already starts in liquid makes it a lot easier to use and user friendly.
So I want to go back to kind of discussion of different types of iron products. We have a question here related to agglomeration, and you talked about nanoscale ZVI. Specific to the colloidal irons, is agglomeration an issue? If so, do you apply stabilizing agents? How do you prevent agglomeration of even 1 to 3 micron size particles?
All right, thanks, Rick. Well, in our manufacturing process, we add organic additives to the material that aid in the suspension and the delivery of the material. So it's more or less a one-shot product. You don't have to add anything in the field. If you look at the iron under a microscope, or conceptually more likely, there actually are dispersants and other organic additives that reside on the surface of the particles that prevent interparticle approach and agglomeration. So it's actually very easy to use. Talking about nano iron, I mean, there have been advances in the nano iron technology where it does suspend better than it used to, but due to the large surface area and the small particle size, you'd have to add a lot more organic additives to make it work, and you'd also have to use much more aggressive mixing and agitation to get the stuff suspended.
Great. So we've got a question from one of our best clients here. So what concentration envelope is Aqua ZVI best suited for?
Aqua ZVI can be used for anything from DNAPL down to low ppbs. That's the great thing about abiotic reactions, is that they'll more or less work at any concentration. Now, I will premise that with the fact that it's not going to react directly with DNAPL. It's an aqueous phase reaction process, so you do have to get the DNAPL into the dissolve phase for the stuff to react. And if there are ways to do that, and if you have questions, you can give me a call and we can talk about that off-site.
Good. Here's another unique question. It's a good one. So for iron PRBs that have already been installed, could this technology be used in combination with an existing PRB to either regenerate it, or in the event the groundwater is moved around it, basically optimizing an existing PRB?
That's another great question, and the answer is yes. There's a couple of ways that could be done. One is that you could actually install another PRB, upgrading it from the existing one, where you'd have smaller, more reactive materials that give you a better distribution than what's often encountered in PRBs. They could act as a sentry, for lack of a better term, down gradient. Another thing with PRBs is that you could consider doing a mixture of the colloidal iron with plume stop. Plume stop is great at promoting biodegradation inside a PRB, but if you add ZVI, you can actually give it an extra kick and get some abiotic degradation as well, and possibly lessen your daughter products that could come off from the PRB eventually.
So we're getting quite a few questions related to DNAPL, so kind of want to go back to that treatment envelope. There's an upper limit, obviously, where this technology can be applied. Could you maybe give some guidance to those folks who are either dealing with residual NAPL? It's pretty rare we see free phase DNAPL, but are you designing PRBs slightly down gradient of those? Are you using a combination? Have there been sites where you've used these with
Yeah, thanks, Rick. As I said earlier, NAPL requires, getting the undissolved phase into the aqueous phase. Iron's not going to react directly with NAPL. And going back to your freshman chemistry, you come to the point where like dissolves like, and NAPL is generally a non-polar material such as PCE. And what the approach that we've tried to do when we had cases like that is actually apply a non-polar substance into the ground that actually will suck the NAPL into the organic droplets, and then it'll be released slowly into the aqueous phase where the reactions occur. That's what happened at the Texas site. I truly believe that when we added the organic, it acted as a sink for the NAPL, sucked it up, and we had the aqueous phase reactions that occur. There was a project called the SABRE project that was done maybe 10 years ago in, I believe, somewhere in Great Britain, where they used bioremediation to address NAPL, and that was more or less the premise. You have to solubilize the NAPL into partition it into a nonpolar phase, and then get it into the water where the reactions occur. So it's a little bit trickier, but it can be done.
So we've got another delivery question here related to, we've had several kind of fractured rock, fractured limestone, basalt. Any special application instructions or guidance when it comes to fractured rock environments?
When we've done work in fractured rock, we've generally gone more or less into straight boreholes that have been drilled into the ground. And what's important is you have to isolate your vertical intervals. If you just pump the material into an open borehole, it's going to find the path of least resistance, and most likely you're going to find most of the material going into the largest fracture in the ground. So it's not that difficult to use packer assemblies where you isolate, say, 3 to 5 feet vertical interval, inject it into the fractured rock, which isn't that difficult to do because the stuff suspends. If you're using large iron, the material is going to sink and end up in the bottom of the column. With the colloidal material, it's going to flow right into the fractures and distribute that way. So I guess the key is vertical isolation for something like that.
All right, couple of questions that I'm going to combine. Could you talk to maybe some of the potential water quality impacts related to ZVI injection? Are there any regulatory considerations that would be unique to this material?
Well, every jurisdiction is obviously different, and every regulator has different opinions as to what's good or what's bad. But with a straight abiotic application of iron, really the only reaction products that you're going to see are ferrous iron, which typically is present natively and is subsequently going to oxidize to iron hydroxide, iron oxyhydroxide, for example, rust essentially, and maybe a slight increase in pH. If you do the metal-assisted bioremediation, the degradation products are going to be the same as if you added the donors by themselves. You might get a little bit of acetone, which subsequently degrades, etc. So there's not going to be anything specific to iron as far as doing a metal-assisted approach.
Good. So we just have a couple minutes left. We have a hard stop at 11 o'clock. Keep your questions coming because we will respond to those. We've got several that I haven't gotten to. I wanted to go back to kind of the fundamentals. And one of the powers of ZVI is multiple pathways for degradation, including the abiotic pathway. It's been my experience that you're going to see multiple pathways, right? So you mentioned the lack of daughter products, or the potential for lack of daughter products. Any guidance to the participants? I mean, we're not suggesting you won't see daughter products. You're just going to minimize them, correct?
Yes, that's correct. There's always going to be a parallel pathway that involves daughter products. The key is to try to minimize that relative to the more direct pathway. The thing about putting iron in the ground is that it will promote bioremediation using the native microbes, sulfate reducers, acetogens, etc., that will take TCE to cis, for example. So that's going to happen in parallel. The key is try to minimize that in relation to your more direct reduction pathway. So that you will generally see a little bit of cis, but the idea is to minimize that.
So we've gotten several questions related to cost. I'm going to try to answer it, and then I'm going to kind of throw it to you to give us some idea on order of magnitude costs. Many of these questions are just, what are the range of costs? How does it compare to other types of iron, other types of technologies? And from my experience, it's so site specific, it's difficult to answer that question because it depends on the site conditions, the types of contaminants, the goals of the project. And our advice has always been, let's put a design together. Let's figure out what the lowest cost alternative is that has the highest chance of success compared to all the other remedial alternatives that are appropriate to that site. So with that as a primer, are there any things that you'd want to kind of add in terms of cost estimating, range of magnitude of cost, things like that?
Well, one thing that differentiates colloidal products versus microscale products is that you generally dose differently. What we dose is a pore volume basis. We calculate the amount of pore volume that's in the aquifer that's to be treated and dose, maybe 5 grams per liter of pore volume. If you're using conventional amendments, they often do it on a soil mass basis. If you run those side by side, our designs typically use about 1/10 the amount of material as like a microscale iron, for example. So the cost at the end of the day is, even though you're using a more expensive material, your overall product cost is less. On top of that, since the stuff's easy to use, your application costs can be considerably lower as well.
That we didn't get to. I promise that we will. I just want to build kind of on the introduction since we had a little bit of trouble. Just really want to welcome you and James to the team. We're really excited. One of the things we're most excited about is our in-house manufacturing, not only of the colloidal iron, but of plume stop. And you touched on it, the innovation that's going to come from that. You outlined kind of the schedule and time frame for production in April of this year. If there are folks on the line that want additional information, you can always contact your local sales managers. We'll have a slide in a moment that has John's contact information, my contact information. We'll be happy to answer any questions that we can. At this point, I'd like to throw it back to Dane, and you're going to discuss the survey options, correct?
That's right. Yeah. Thank you, Rick. That does conclude our presentation for today. If we did not get your question, as Rick said, someone will make an effort to follow up with you. Just a couple of quick reminders, as Rick mentioned. First, you're going to receive a follow-up email with a very brief survey. So we really appreciate your feedback. So if you could, please take a minute to let us know how we did. Also, you will receive a link to the recording of this webinar as soon as it is available. If you need immediate assistance with a remediation solution from REGENESIS, please visit regenesis.com to find your local technical representative, and they'll be happy to speak with you. Thanks again very much to our presenters, Rick Gillespie and John Freim, and thanks to everyone who could join us. Have a great day.